Hi, I'm Bernice.
Hi, I'm Rashia.
Hi, I'm Serby.
As students at the University of Virginia, we receive many notifications of crimes reported in the Charlottesville area. In this project, we aim to use machine learning to see how different factors affect the types and frequency of crimes. Since higher rates of poverty are usually associated with higher crime rates, we hypothesize that a higher unemployment rate would also prompt higher crime rates. The idea stems from the notion that without a steady income, people have a greater incentive to commit crimes than those who do not. Understanding the relationship between crime rate and variables such as unemployment, population levels, resource deprivation, regions, and time will allow us to plan the most effective way to make our state as a whole a safer place to live.
Other factors include drug problems, lack of education, and poor quality health care. Although the state is aware of these issues, an increasingly impoverished population may lead to higher levels of crime. Although no large trends have shown up yet, Virginia's 2017 crime report shows that drug and narcotic arrests have increased 15.6% from the last reporting period. Motor vehicle thefts have increased 3.9%, and hate crimes have increased 47.4%.
Our data included various different factors from area codes and population sizes to crime rates for burglary, larceny, motorized vehicle theft, and robbery. Preliminary experiments showed very scattered values and no conclusive trends were found. The data was then grouped by year and the median values were calculated accordingly. This provided a much cleaner trend that could be followed. The graph showed that as the median value of unemployment increased, the median value of the crime index also increased.
Then, we used clustering to perform some analysis on the initial data. First, we plotted the number of clusters versus the score of the k-means algorithm on the data, and then determined that 30 clusters was the ideal number of clusters before the score started plateauing. After we used the 30 number to aggregate our data into 30 clusters, we then performed the scatter matrix program again, and then found that there were much stronger correlations between the variables.
All of the quantitative crime features had already been compiled into a crime index feature, which was used as our data labels. The scale for the crime index feature is approximately 1,000 to 8,000. Features such as population, year, area code, and unemployment rate were used to construct models that could accurately predict the crime index. 3 regression models were trained. We first ran the linear regression model and got an RMSE value of 1,379.64. Then we ran the decision tree regression model, and we got an RMSE value of 1,431.86. Finally, we ran the random forest regression model and got a RMSE value of 1,335.74.
Ensemble learning was used to reduce the RMSE by training several models and combining them into one predictive model, therefore reducing variance. The RMSE values went down after using the ensemble method on the random forest and decision tree regressors, but the values were still fairly high.
In order to achieve a better RMSE value, we conducted group search on our random forest regression and were able to achieve a residual mean squared error value of 377.70 for our final prediction model. This was our best RMSE value.
Population and region seem to have the biggest effects on crime rates, as shown by the weights of the grid search. Unemployment did not have as much an effect on crime as we had hypothesized. These feature weights make sense because they had high correlations with crime index when we performed clustering earlier on. This provides a deeper insight on how to tackle the issue of high crime rates in Virginia.